Hi, I'm Blake Sanden. I'm the Irrigation Soils Farm Advisor from Kern County near Bakersfield, and we're here today to talk about efficient citrus irrigation. Now, don't think I'm going to sit here and tell you how to irrigate your citrus. What I'm going to talk about are the things that you need to start to put together to provide for the most optimal management system of information and field monitoring so that you can get those 800,000 boxes per acre, right? Okay. What's the critical process that keeps the crop growing? Optimal photosynthesis, maximum carbon dioxide uptake, and right here is where that happens. This is a micrograph of the underside of a leaf. Those little porthole goodies that you see kind of in the middle right here, those dudes are the stomata. When they have good water status in the plant, they're wide open. And guess what happens when they're wide open? That gives you a porthole for your water vapor, the transpiration, the water use of the plant to leave the plant. That is also how the carbon dioxide gets into the plant to make your carbohydrates and your overall plant structure. If you're an alfalfa plant, this is pretty much how it works. CO2 assimilation on the left-hand y-axis here, and we've got stomatal conductance on the right-hand side. Straight line relationship. As you assimilate CO2, you build your carbohydrates. If you're an alfalfa grower, you build the tonnage of the hay. If you're an orange grower, you need a good chunk of this, especially if you got an 800 box crop on the trees, because you have a lot of vegetative matter that you need to build up in that fruit. It's not quite more water equals more yield, but less stress equals better carbon dioxide uptake. And when you get at the field level, this is the kind of strategy you as a grower are being asked to put together. And I can tell you for a fact, of a lot of the engineers I work with across the state in the water, land, the oil industry, none of them have the same level of complexity to deal with that you do as a grower. Everything from the aspects of the proposed crop, the variability in rooting characteristics, life cycle, and water use. I look at all the varieties of citrus we have. It's a huge variability, down to the variability of the natural factors, soil, topography, water quality and chemistry, fertility, and then we come over here, we engineer the irrigation system, how much we put on, how quickly it goes on, and you know, how wide it spreads, a little dripper or a big fan jet. So you have a tough job to do as a grower. But the principle of what we're going to focus in on today is right here. This cup, determining your water balance. First, what it means is you have to know your soil available water, and that's a textural soil kind of thing, the distribution of how far your drip or fan jet pattern goes, how thirsty is the crop, and how often do I fill the cup. So with that idea, there's got to be a better way than this to find out what's going down in the root zone. I'll tell you what though, when you start doing all of these things, you're going to feel about like that guy that's spent years with his head in the dirt. It's a three-point sermon today. We don't have time for the irrigation crop salinity tolerance issues. We're going to look at understanding the soil, developing that water holding capacity, how you monitor that, and crop water requirements, stress in citrus. So when you dig a backhoe pit in your field, you could come up with all kinds of different layers, hard pan, caliche zones, little stringers of silt, and excessive silty area versus sandier areas where more roots proliferate. It's imperative that you understand that and borrow a neighbor's backhoe pit, whatever you have to do. It's easier than just using an auger to try and get down there and see what you've got below. But you can do that with enough experience. And then once you have that idea of the different profile as you go down in that backhoe pit, citrus rooting, really top-notch loamy soil, you're going to have roots down to 4 to 5 foot easily. Then what you do is you determine your soil texture. Using this feel method, you wet the soil up, you see how long of a ribbon that you can make, and the available water holding capacity we often define either in a percent volume, that's what you see in scientific papers, Or more practically, we look at it as an inch depth of available water per 1 foot depth of soil. That means if I've got 1 inch per foot of available water to my citrus tree and I got a 5 foot root zone, it means I've got 5 inches of water to work with. Pretty simple, right? And in principle, it is. To put all this information together and make it practical for how you irrigate your field, that's another matter. Basically, you can come up with 4 categories of texture: coarse, sandy, medium, fine, and you'll get everything from about 3/4 of an inch per foot depth of soil, available water, up to 2.5 inches per foot. These kinds of tables are also prepared and provided to you in this presentation here, so that you can go out and actually push your soil probe in and feel how that soil either makes a ball, makes a ribbon, or doesn't, falls apart, and this will give you an indication of how much available water is still in that particular profile. So let's key in on where we're going with some of the on-field maintenance of these issues. There's more information with respect to understanding this soil water holding capacity issue in another presentation in this series, Field Irrigation Monitoring for Maximum Efficiency. Now, we're going to get down to put in some of the engineering aspects of what we can do with systems. What about a fan jet? These, of course, are almonds here. And if I'm on a really sandy soil, fan jets make sense. I spread the water, gives me a better distribution. But what if I've got, kind of like this here, but what if I've got a loamier soil, and this is the same orchard, by the way, where I put in a double line drip? Well, gosh, my surface wetting pattern's this tiny little donut. Is that all I've got going all the way down? Well, absolutely not. This particular field here, we have analyzed the distribution of that water out across the field, and we basically have a subsurface storage right here of available water holding capacity that gives us a reservoir almost identical to that fan jet micro sprinkler system you saw. And it's because there's enough capillary subbing in this ground to, here's our dripper here, to really pull that water out and give you this beautiful inverted mushroom that gives us about 30–40% volumetric storage. Another table provided to you in this particular presentation is this one here. Here's the 12 USDA soil classifications from coarse to fine, the approximate available soil moisture in inches per foot, and the average drip subbing diameter. If my drip starts up here on the top, and if I go down to about a 2 foot depth in the soil and dig out to see where the limit of my subbing goes to. In a sand, loamy sand, you're only going to get 2 to 3 foot. But you go down here to clay loams, silt loams, silty clay loams, you'll have a diameter that's easily 7 or 8 foot across. You got a double line drip system that's 4 foot across. You have 50% of your orchard floor that will sub up with water. And then why is that important? If I have a breakdown, I'm trying to understand, well, should I run 6-hour sets, 8-hour sets, 16-hour sets, run on off-peak, or 24-hour sets? Here's a guide that indicates how long it takes to refill that profile, given these two different systems. Double line drip, 10-gallon-per-hour fan jet, 14-gallon-per-hour fan jet. I'll let you chew on that later. We have to go on to the next topic, which is irrigation non-uniformity. One of the single most important things you can control in your field is how uniformly that water is spread out across the field. Now, you can see this example is flood irrigated alfalfa, and we got problems here at the end of the check. You're at the mercy of the infiltration of the soil compared to these engineered micro sprinkler systems on these uniform almonds next to it. What that basically is this concept of distribution uniformity. DU in percent equals 100 times the average infiltration, like right here, in the dry quarter of the field over the average infiltration for the entire field. So where that puts you is in a situation where if you haven't done a good job in your microsystem making sure that you have uniform pressures on all your various subunit valves, and you end up with an area where you get a really high pressure and you have a non-compensated dripper, as in this case, you can end up with a lot of excess waterlogging and eventual phytophthora and problems with your trees. These little guys right here, hose screens, a number of irrigation companies recommend them, especially with drippers. If you have a break in the sand media tanks, the filter, you don't want it getting into your system. These are good to prevent that, but they also collect algae. And this algae across here, if you're not chlorinating your system, can drastically reduce your pressure and really drop your uniformity. Now, the uniformity is important not only for even application of the water, but your fertilizer too. If you're like most guys, you're on kind of maybe a 4 or 5 time fertilizer squirt throughout the year, 20% bloom and 30% mid-season a couple of times, 20% post-harvest. Well, that uniformity aspect is going to hit your fertilizer application as well. So here's a kind of a hypothetical situation. 90% DU. This used to be considered, about 15 years ago, this used to be considered almost impossible at a field level. But I can tell you for a fact, there's a lot of my Kern County growers that have system uniformities of 90 up to 95%. We made tremendous strides in infield pressure regulation and distribution. This over here, 70%, used to be considered real good. But look at what happens to your 150 pounds of nitrogen on that 70% uniformity. The average of your wet quarter, not the wettest part out here, this is getting 250 pounds, but the average of your wet quarter is getting more than twice the nitrogen and more than twice the water as your dry quarter. This represents nitrate pollution, and we've got the Irrigated Lands Regulatory Program coming on, and it represents lost water. It represents disease over in here, represents the loss of maybe 300-400 boxes of yield down here. You want to get to be the most uniform that you can. Okay, moving on to the second point of our 3-point sermon, monitoring soil moisture and irrigation uniformity impacts. A push probe is really handy for kind of checking, okay, where am I at? Especially if you don't want to be dedicated to one spot and you know this part of the field is a little more vigorous than this other part. You buy yourself one probe, you dedicate yourself to checking those sites. That can be really helpful. Neutron probe contract services, there's a few of them out in the valley. These will give you a hard number, the largest volume of sampling of any technology out there. But you're lucky if you just get one reading once a week, and you're of course at the mercy of the service provider. Tensiometers, you install it, you don't have to hammer any holes except when you put it in. You go out and you check it, unless you forget to service it and keep water in it. And it'll give you an indication of the tension that the tree experiences in extracting water. These little guys right here, these Watermark blocks, I like to glue them on the end of a piece of PVC, and you can install them very similarly to a tensiometer. Put them at several depths. They're electrical resistance blocks, and you can hook them up to a variety of different loggers. There's also these capacitance probe sensors, PureSense, John Deere Water, Ranch Systems, AquaSpy. There's a lot of these out there right now. A whole bunch of different loggers. You can, you can start to get a headache trying to navigate through all this stuff. Then you also have to decide, wait a second, I've got a fan jet on this block, I got a drip system on this block. Well, where do I put my monitors? Me, myself, if this is the fan jet right here, I like to go along the berm, so I'm not going to hit it with a piece of equipment, about half the way from the fan jet to the outside edge of the circle, put my monitoring device there. Double line drip, if I've got about a 3 to 4 foot spacing on the drippers here and here, then I like to come right in the middle between those drippers and put a tensiometer there. If I've got more space out to the side, I like to come, and Watermark Blocks, I like to come and put another couple 3 foot out to the side with those sensors. So we'll go through an example real quick of installing some Watermark Blocks in a citrus orchard. This is a fan jet system here. You can see we put in one of these Hanson AM400 loggers. I've got a 15-inch and a 30-inch Watermark installed right here. The fan jet system blows about 2.5 to 3 foot beyond these sensors right here. Okay, probably your least expensive options out there for hooking up Watermark Blocks are these two guys. This is the Hanson AM400 logger and the Aerometer logger. Looks kind of like your kid's lunchbox. This one I kind of like because it's the only logger out there with a graphical display that shows you what's happening with the water content without having to download it to a computer. The Aerometer loggers and a lot of the other offerings out there, you get a number of where you're at right now, but you have to download it to a computer or have web access to see where you're actually at. So let's push the button and take a look at a few water monitoring patterns. This is as I said before, 15-inch, 30-inch depth. You can see the irrigations here are almost perfect because you go up to where you virtually saturate out that 15-inch depth, and then the water passes through there and then just perfectly refills the 30-inch depth. If you look up here, see those sharp peaks? Those are drainage out of that. Now, there's no way that you can see this kind of pattern and know when you're blowing water by that zone unless you have some kind of continuous monitoring. So you can see that shape of that pattern of your water flow all through the irrigation. Here's an example where these two systems are on the same row. This one is down at the bottom, and this one's up higher up on the hill, about 10, 12, maybe 15 foot elevation less. You can see the irrigation here is virtually perfect. I'm just recharging back to 30 inches using the water right out here. In fact, you can see we waited a little long between irrigations out here, but look it up here. I have this is a fan jet, non-compensated, and I've got about 5 PSI more energy up here. And what's it doing? It's driving more water. So look at this 20 to 10 centibar water tension all the way through here without a break. That's a formula for potential Phytophthora in that area. And you're blowing water by the 30-inch depth virtually every time. So you got to get in there to that lower area, reduce the pressure on your submain so you can avoid some of this. Here is a grower who had a drip system who just kept it on all the time, way too wet. Another little bit of pressure irregularity in another place, but even here you can see this was too wet all the time. This one shows some benefit with a gypsum application that we had back here in the last couple irrigations before harvest cutoff in these almonds. This is a huge amount of stress defoliation on these almonds, and this area didn't have anywhere near as much defoliation. Okay. Let's say, I don't want to mess around with having checked this stuff in the field. I want to hook this stuff up to the web. You can spend $5,000 to $10,000 on a site-specific monitoring system and have that ported up to the web. Is that degree of detail going to tell you that much more than the patterns we looked at before? That's debatable. This can be really useful for some research stuff. In this case, they had a sensor every 4 inches, 4, 8, 12, and then actually I think this one's 20 inches here. You can see the daily water use. Here's the night. The stomate shut down at night, no more transpiration, and then whoosh, sucks it out during the day. You as a grower, debatable on how much detail you need, but one thing for sure, you need a better method than this one. A seat of the pants is way too common of the usual tool that most growers are using out there. Now we'll move on to the third and really critical part of our presentation, crop water requirements, ET, California Irrigation Management Information System, CIMMYS, and plant stress. This, of course, is where the rubber meets the road. Crop ET is E, evaporation, that's from the wet soil. T, that's the water that blows out those stomates that we talked before. And it's really interesting. We haven't been out of the cave that long with our modern agrometeorology. Really only the last 50 years or so have we improved in our developments of understanding potential evapotranspiration, as in this case from a well-watered pasture grass crop, and then how that fits in to planning our overall understanding of crop water use out of the year. This is just over a period of 6 years, from 1993 to 1999, the estimate of average potential ETO, that's that grass water use per year, went in the Central Valley of California, southern San Joaquin Valley, went from 49.3 inches to 57.9 inches, an increase of 9 inches. And that's not just global warming, guys. I mean, that's a better understanding of how to use the science we have for this kind of system. CIMMYS has done a great job. It's a free service available to anyone looking at water use. They have a couple hundred stations all around California. Just punch in CIMMYS in Google and you can get online and check it out. They have average water use tables for all of these various areas out across California. Most of the citrus area is kind of down along this zone here, some of this region 12 and also this region 15 and 16, where we have an ETO that runs 53 to 50 to 62 inches a year. Here's how you use this calculation. The ET of the crop is potential ETO times the crop coefficient, Kc, right here, times some kind of environmental factor. Maybe a little salt problem, maybe a little additional vigor of the crop. And if you take our normal year ETO in the San Joaquin Valley, multiply it by this crop coefficient, this is mature citrus, runs about 0.75 in the fall, spring, gets down to about 0.65 during the summer, and then you come up with what you would expect a weekly amount of citrus water use to be. So pushing about 40 inches for a good, healthy, vigorous stand of citrus. So let's look at a brief example. What is optimal? Is that 40 inches absolutely optimal all the time? Well, here's an orchard in Tulare where the grower was under irrigating, where he only would use, in this case, 34 inches from March to October the previous year. Rainfall provided a little additional and moisture storage water use. He got 38 inches, but he finally listened to the researchers studying this field, put on 50 inches the next year. A little bit of overkill, but he had a little bit of salt he had to push out too. 45 inches of ET, 12% more ET than that classic 39 inches. And he reaped the fruit of that by pulling in more than double the box count of his neighbors in Tulare County. So why is that important? Wait a minute. We have a table that says it's only 39.5 inches. Why did it use 45 inches? Well, different varieties are different soils have different capacity. The weather will change from one week to the next. We don't have data on this, but quite possibly the fruit load on the citrus tree can potentially make a difference as well. So you observe the plant stress, listen to recommendations of your farm advisors and others, look at the fruit load, and be ready to come up and deal with a different amount of water if you have to. Well, just a quick results on the early Beck trial in Kern County. I'm going to focus on this 2007 data here. We called this our 100% ET, 42.6 inches, 31 inches with 73% of that, and we had a 25 inch. This is RDI, trying to bring on early color. Yeah, maybe take a little fruit size hit, but if we can be the first ones on the market with early Becks, you got $2-3 more a box. So we were measuring stem water potentials. This is how you check the actual stress on the tree itself. You take a leaf, you put it in this lid here, put it on this pressure chamber, and you crank up the gas to see just how much pressure it takes to get the liquid back out of the xylem. This is what it looks like on an almond stem. Here's what happened with that particular trial we did. You can see in 2006, we didn't have near as much separation as we did in 2007. Why is that? Well, 2006, with the reduced water application, we dried the reserve out of this root zone even more. So we had extremely high stress conditions. Bottom line, as a citrus grower, if you want to have no stress on the trees, you want to run somewhere between this -12, -10 bars of pressure. That's 10 bars of pressure is 140 psi. And as soon as you get down here where you're 14 bars and below, you're really increasing stress. You increase stress, you're going to decrease your stomatal conductance, you're going to decrease your ET, you're going to save water, but you're going to start having trees that look pretty tough, and you're also going to lose yield. This is what happened here. Here's the pounds of fruit per tree. We had 261 pounds at that low irrigation treatment, 358, and we had absolutely no benefit for bringing on earlier color. So the grower's best treatment in this case was this full irrigation and not to give up that kind of box count. So what it boils down to is how do I put all this stuff together? You've got to go to your field, treat it like an electric motor. I've got all this boilerplate. I need to know the horsepower, the acreage, the capacity of my irrigation system, how much flow I can put on per hour, per day, what's the depth of that water, how many sets, and then a way to understand what are all these critical factors. I'll let you guys read this a little bit at your leisure later on, but here's what you're going to shoot for. You need to put together some kind of checkbook so you can balance your irrigation scheduling. Here's all these components of your system characteristics, your refill depth, how much I put on in terms of the inches per day, right here, the application, and then some way to track how many hours did I run in these various weeks, and where does that put me in terms of penciling out my available water. This is online. This is a whole nother session to explain this guy. And however your sheet looks, get organized so you can see where that water content is going, because the technology is helpful. Get those soil moisture sensors, but if you don't have it combined with how's my irrigation running, where's my plant stress at, and where's my yield tracking from one year to the next, you're going to miss a boat. The bottom line is, if you get $60 water on 150 acres, 6 inches isn't a big deal, $4,500 bucks. Of course, it's not $60 water this year. $500 water, that's $37,500. That's a chunk, but if you get 150 boxes of 88s in addition to that at $2 net, that's $45,000. That, water savings, you may actually use a little bit more, but tune up the pressure, pay attention to those distribution uniformities, get as uniform as you can possibly be. And in the end of the day, the picture of that water use, the organization of your water content is not just worth more than 1,000 words. It may be worth way more than several $1,000s. Thank you for listening.